Yeah, you tried to. Okay, master cylinder was there, and nobody carried. Or, no, the master cylinder. So makes both. Well, no. So here. I do that, slow it way down, but if I pull the brake really fast, it feels like I slam on the brakes for the first maybe split second of each pump. So I had to slam the brakes 5 times. So that's how I got here. Yeah, I'm very smart. I'm like that.
Yeah. That was me. That was me. I didn't know if you were like, who's that? Who's that? It's our fan.
Well, I was going to leave it on low.
Oh, okay.
I mean, normally I leave it on low, but is that a problem?
No, I don't think so.
See if that's too loud. I know high is way too loud. I didn't take off because I did something that wasn't needed. I just found out didn't need to do all that.
Yeah.
That was not what was asked. I didn't like it for anything like
that. Okay, here, this is an eraser mark. So,
wait, what?
Oops, this little line right here, it's not supposed to be there.
Wait, which one?
That one.
Oh,
that
no.
looks kind of like a negative sign. Yeah, no, that's supposed to be erased.
Oh.
And then, what does that even say?
Oh, he wants you to write your intervals.
Sammy, I got the values correct, and I didn't think those were right because of how weird the number was. So then I just didn't do the rest of it.
Brittany!
I ran out of time and then
Which one?
I ran out of time on the last one, but of all the ones that ran out of time, I'm glad it was the last one, because I don't think I got much of that one right at all.
No, me either. I didn't do.
Because when I got to this point, that was my first derivative. So when I take my
I
second
end up?
derivative,
I was just like,
product
yes.
equals to some rules, and I was like, there's no way
that.
I can
Pan back some. Or zoom back some.
start writing it.
The
and I'm
camera?
like, "That's
Zoom in or out?
Yeah.
Zoom out. Because
I didn't even, I got a function, but it's not even right. So.
Yeah.
Oh well.
Is that good?
okay, that's good. Thank you.
Because those aren't parentheses, those are brackets.
Almost got it out?
Almost. Do you see this? Almost.
You put a star by it.
He's just like technically.
I would really like to get a decent grade on
What did you
one.
get on this?
It's okay. Terrible. I didn't do it terrible.
I got
And that's
90 out of 100.
That's a decent grade.
It's a C.
all my pre-calc.
Then what is
Okay,
that?
so
An F?
let's go ahead and get started now.
Yeah.
Have your
Yep, third one in a row.
I missed one
test
of
back.
the mistake. I misclicked
I
one
just-
time.
So, go ahead and establish that the due date for the test rework corrections is Monday.
And I even put plus.
Get that done.
I'm
Uh,
gonna cry.
Couple of comments about it, about the test.
Wait, so
Well, we'll make sure. Hopefully there's comments. On
so would you just put it there, or would you actually have to put
on number 3, there's more than one interval that satisfies Rolle's theorem. Numbers 4 and 5, they were pretty straight up, but a few people neglected their rules of differentiation. That's stuff on number 6. It's very similar to one we did in class, slightly different, but most of us knew how to attack the problem, but then got a little stuck when it came time doing the local derivatives. So, on that part, on number 7, 8, and 9, you only had to do one piece, one number, one item off the graph and guideline sheet. So, like number 7, you just had to do the stuff about asymptotes. On number 8, you had to do the stuff about the first order. So what would be included in first order? Look at the graph and guideline sheet. That would be you have to find the intervals of increasing and decreasing. So you have to literally give me intervals. Answers are it's increasing on these intervals and decreasing. You also have to identify local maximums and minimums. And those are the things in the first order stuff. The second order stuff on number 9 is again only the items from the second order part on the graph and guidelines. So you had to find on number 9, you were supposed to find intervals of concave up and intervals of concave down, and any inflection points. And, so again, some people kind of did a part of it, but didn't quite do all of it. So that just so you know what you need to do on those. On number 10, we had to draw a graph. Some people got a little careless on their intercept. I gave you one intercept, f0 = 0. And some people had more than one intercept, so that's clearly not following the plan there. Also, you've got information about asymptotes. So make sure you take those into account. And then 11 and 12 were the kind of do-it-all problems. And once again, on the do-it-all, you have to do all of what's on that graph and guideline. So you have to find x and y intercepts. You have to find intervals of increasing, decreasing, local max midpoints, intervals of concave up and concave down, and inflection points. So all of that has to be identified in your work on numbers 11 and 12. Number 11 is not too difficult, other than the numbers don't come out to be integers, but that's okay. They're not that difficult to find. Number 12, I will concede that number 12 is when you get to the second derivative on number 12, finding when the second derivative is critical, meaning when it's equal to 0, is difficult because it's a cubic function. But you had a calculator on your test, so how can I find the 0 of a cubic function with a calculator? Yeah, you use your calculator, you can find the 0 of that function easily. It'll be some decimal number, but because I don't have a cubic factoring formula like I do for quadratics. That was the only thing that was a little bit beyond, but that's one reason I'll let you have a calculator so you could do that part of it. The rest of it is on $27 calculator. Okay, that's about it on comments. So again, the rework, if you choose to do it, is due on Monday. Questions real quick before we So I guess no questions here. We'll go on to the next block of material.
But I don't, it just relates to engineering, and I've been interested in it because of robotics, but I've never understood it. So I think it would be cool.
Block 7 is where we're going to apply derivatives in a real-world type of setting.
You have a question, Dale?
Question, yeah. Josh? Josh.
On paper 2 of the test, number 2 of the test.
Huh?
How would I math in that? Go you there.
Okay, so for number 2, the C value, it wouldn't work for the negative value because it's not within the interval.
Correct.
So I just didn't put the negative value. Do you want it simplified in like 2 over root 3, or would you accept the square root of 4/3?
Square root of 4/3 is fine. I was looking for that you had shown that there were 2 possible answers of C, but only one of them fell in the interval.
Okay.
A lot of people did that. They go, I got this plus or minus, but only the plus is going to work. So I erred on the side of not giving you the benefit of the doubt this time, that if you just put the plus, I could have erred and said, oh, well, they knew that it was plus or minus, but they only did the plus because it fell in the interval. But I chose this time to err on the other side and say, well, they didn't tell me, so did they just assume that the square root was automatically positive, or did they know that it had to be equal 1 and then had to choose which one was correct? So this time I took off a point for that on 2 papers because they didn't show me both the plus and the minus and then choose the correct answer. Does that answer your question?
Yes, thank you.
What question? Someone else have a question? I guess not.
Crap, I was so close, Sammy.
You know?
What?
I was so close, Sammy, on the last one. Like, almost.
Which one?
The 12.
I almost had 11.
Yeah.
What did you get wrong in 12?
In chapter 3 still. We're good now? Ready to begin? New material? That's called questions on the test. So I don't want to stop in the middle and go back to the test. Last call, test on questions. Okay. So we're going to start on block 7 today, which is on applications of the derivative. Optimization is section 3.4. Related rates is 3.5. So those are the only two sections we're going to cover in this block. But they're all applied problems. The terminology ought to indicate something to you. Optimization, what does you think that means? Optimize. Make it better, and not only just to make it a little bit better, but to find the best. So optimization is about finding the best. So that might be something like maximize, minimize time to produce something or do something. Minimize costs, something like that. So to find the minimum or find the maximum on some function is what we mean by optimization. So that ought to indicate to you how that ties directly to derivative. That's what we do today. But then the other section is related rates. We'll just go and mention, what do you think about that? What does that potentially mean, related rates? Yeah, something like that. That's another fairly example to understand is imagine a ladder. This is a classic example in calculus to understand related rates. Imagine a ladder leaning against the wall, and if the bottom of the ladder starts to slide away from the wall at some rate, then the top of the ladder is going to slide down the wall at some related rate, not necessarily the same rate. Okay? So when something's changing, then something else is also changing in a related fashion. That's what that means. But rate, right there, ought to tie to derivatives in your mind, because the rate of change is the derivative, right? So we're going to be using derivatives in these games. So now to do optimization, that's what we're into today. We're going to be kind of a big picture of it is, we want to, so in section 3.4, we want to optimize called our objective function. And then subject to will have some kind of a constraint and then it needs to be on some domain interval. Why are all those pieces important to me? And then we'll do some examples here in just a moment. So let's suppose I want to maximize my revenue of selling refrigerators.
Shrimp?
Well,
Is that what you said?
one thing you could, the obvious answer is we'll just sell more. And that's true. The more you sell, because each refrigerator you sell for $1,000, you make a certain amount of revenue off that. So you sell more refrigerators, it keeps going up. But if that's the case, if that was just all I had to do, and there were no constraints in the world, what would that mean? What would be my maximum revenue? Well, in some sense, it'd be almost infinity, because you could just sell unlimited numbers of refrigerators. But is that how it happens in the real world? No, I mean, if you oversell refrigerators, then you glut the market and the price goes down. So now you can't sell them for the same price as you were selling them before. So there's a constraint there. There's these what we call conflicting constraints. One thing goes up and the other goes down. And you want to optimize by getting those things somehow matched up in some fashion. And so that constraint is important because that keeps us from making it just unlimited. And then also the domain interval is based on how the real world applies to the particular problem you're dealing with. Okay? And we'll see that in a fairly simple example. We'll start right now with a simple example. Again, a classic type of example to understand optimization types of problems. So let's say you want to maximize area of, and I'll show a shape here in a minute, of a field given 1,000 feet of density. And so the field that I want to maximize the area on, I want to build a field pasture for my animals. I want it to look like that. So I want to fence off sections of a field so that I got three distinct areas in my pasture. But I want the maximum total area, and I've only got 1,000 feet to work with. So how can I do that? What's the maximum area? What would be the shape of what would be the dimensions of this that give that maximum area? So what you want to find here is find max area and dimensions and give it. Okay. To attack this problem, we didn't understand how we're going to do this. So I'm going to take a moment. We see the basic problem, very simple problem, but I'm going to go over to the other board here and talk a little bit in general about how do we maximize something, how do we optimize, what do we really do to do that. So that's the problem we're going to work on, but let's talk a little bit about it. Okay, so how might I maximize? What do we mean to maximize? Is that the local maximum or is it the global maximum? When I say maximize the area, is that going to be the overall global maximum of area or is it going to be the local maximum of area? It's going to be the overall global maximum of area. So that's the first thing we need to understand. In optimization, we're looking for the global, not the local maximum area. Thing to understand. Is that clear to everyone? I want the maximum. I want not just the local high point, but I want the highest point possible. Okay, on a graph. Now, how do I find that global max or min? Well, there's some things to consider. I consider some potential graphs. Okay, this is an interval from A to B. Well, the graph might look something like this. On this graph, do we see where the global maximum is and where the global minimum is? First of all, where's the global minimum on my picture of this graph right here? at A. So this is my global minimum. I agree. That's the lowest point on that graph. Where's the global maximum? It happens to also be a local maximum right here, like global max, which happens to be a local max as well. But the point was that the global minimum was not at a local minimum, it was at an endpoint. Okay, well, how could that change? You can add something that looks like this. So I'm building an objective function. This is my objective function I'm looking at. I've got a domain interval, and somehow the constraints involved, but we'll come back to that. I've got a domain interval here. I've got an objective function. So where's my global maximum on this one? Right here at the height of that local max. So my global max and my local max are one and the same this time. Okay. What about the global minimum? There is none.
Oh, cool.
Why is there no global minimum? There is a local minimum, but there's no global minimum. Why?
That's designed.
Yeah, there's no lowest point. I mean, if that number was a height of 1, you're not actually ever hitting height of 1. You're hitting 1.1, or you're hitting 1.01 or 1.001. So there's no lowest y value. So there's no global minimum on that picture. If you have an asymptote, you're going to have the same issue. You had something like this. What would you say about global maximum there? No global max, because it has an asymptote going up. So an open end might cause a problem. It might not. So there's no global max. The global minimum is right here. But let me go back over to I could have both and still have open ends on this. Let's see. Here's another example that would work with open ends. So having an open end doesn't preclude it. So you can have an open end here, then maybe go up and then back down, and back up, some other open end. Now you do have a global max and you do have a global min on this picture. Both of them are at locals, local max and mins. The endpoints are not included, so I can't even consider them. So what's going to be our criteria for finding these global maximums or minimums? That's what we mean by optimization, is to find the global. So what can you observe from these pictures of how and where we might find the global maximums or minimums? When we had a global max or min, where did you find them? Yes. The global max either occurred at a local, if there was one, or it occurred at an endpoint, if there was one that was included. Okay? Anytime you saw a global that occurred, it was either at a peak or valley, it was either at a local, or it was at an included endpoint. Okay, well that's nice to know. So we can start with that. Let's see. So our plan is going to be right. your function. Come back and actually do a problem. I just kind of build up to how we're going to do it. And once we have our function, oftentimes the function will have multiple variables in it, so we'll use the constraint. We have to also apply the constraint. Which will usually, this will help us to create a function that's only one variable. And then now we're to the point of we've got this function, like I had a function graph over there. How do we find this global max or min? What did we say? At the local max or min, or it's at an endpoint. So first we've got to find the local max mins. How do you find the local max mins? Got to have the first derivative and find the critical values. So now you got to find first order critical values. That's easy to do. We know how to do that.
Yeah.
How do you find first order critical values?
Wherever the derivative is equal to 0 or it does not exist.
Correct. And then the final step of the puzzle is simply to check which of those is the biggest and which of those is the smallest. So you're simply going to you're going to evaluate the original function at the critical values and domain endpoints. And the biggest or smallest of those set of values is your optimal, like we saw over here. The biggest point was here, so that will be at a local maximum, and we would see that when we evaluate it. The lowest point on this graph would be at that endpoint. If I do f of a, I'm going to get some number. If I do, so that, again, graph idea is, from what we just said, you're going to calculate f of a, you're going to calculate f of b. My pen's not working. So you're going to do f of a, f of b, and then you're going to also do any interior critical values. So you're going to do, let's call that c and this d. You can also do f of c and f of d. And which one of those is the biggest will be your overall maximum, and which one of those is the smallest is your overall minimum. And then that's your answer to your question. So it's really quite simple. Okay, well let's move back over to this board and see if we can set this original problem that I posed to you. That's a classic calculus problem for applying optimization. Let's see if we can set that up. So I'm going to redraw my picture over here so I have something to work with on one board. So we have my objective is to maximize area, and then our subject to constraint. So I use ST for subject to. What constraint do we have on this?
1,000 feet of fence.
We have 1,000 feet of fence. And we'll have to figure out the domain eventually. I don't know that yet, but we'll come back to that in a moment. Okay. So we got to start writing a function from this point forward. So I need some variables of some sort. Now, one thing I did not indicate to you that I really do need to indicate, I intended for the, say, 1/2 of the overall length here and here. This is the width. I didn't indicate it. It could have been a third or fourth, whatever. I didn't indicate it. So I need that to, I need something there to know how far to put this bar in. Okay, so let's assume it was 1/2 of the length here and 1/2. Okay. Let's start by writing the overall area of, we want to maximize area. So let's start by writing an area equation. So area is just equal to the total length, which is L, times the total width, which is W. There we go, we have an equation to maximize. But a function of one variable, that's a function of two variables. Yeah. So that's where the constraint comes in. What's my constraint? Let's write our constraint equation. This is my objective equation. Now let's go over here and let's write my constraint equation. I need an equation that tells me about the fact that I've got 1,000 feet of fence that I can somehow use in my function to create a function with only one variable. I couldn't hear. I'm sorry. Speak up. Yeah, I've got to have the total fence equals 1,000. Okay, so how do I figure out the total fence? I can't hear you.
It's given.
Well, it is given. I've got 1,000 feet of fence, but in terms of the geometry of this picture, how can I determine 1,000 feet? I mean, I got to put this here, here, and here, and here, and here, and here, and here. I mean,
oh my gosh. Do you want to add like the individual pieces?
yes. I've got, half L and a half L and a W and a half L and a half L and a W and a half L and another W there. Like I've got 1, 2, 3, 4. So I got 4 of half L's plus 1. Oh wait, more than that, 5 of them. I have 5 half L's. So I got this right there. So it's 1, 2, 3, 4, 5 half L's, and it's 1, 2, 3 W's.
W. Gotta take the W.
Do you follow this now?
Yeah.
Why is that important? Again, if I wanted to maximize area and I had unlimited fencing, all I have to do is fence the whole world, right? But that's not real world. So we're going to be limited to 1,000 feet of fence. That's going to allow me to, if I use this constraint equation, that's going to allow me to convert this to a single variable function. So which variable do you want to work with? W in here. Which variable do you want as your variable? W or L? Doesn't matter.
Can you use the dub?
W. Okay, so what do I got to do over here then if I'm going to keep the W? So for L here, I got to replace L over there. 5 halves L equals 1,000 minus 3W. So L equals 2/5 of 1,000 minus 3W.
L equals 2/5.
So therefore, with this constraint equation that I've just written, I can write this as a function of W. That's what Rezo wanted to use. So since it's Rezo's special day, we'll go with W. Yay. So A of W is now a function of one variable, which is L, 2/5 of 1,000 minus 3x, not that x, I'm sorry, 3w,
3W.
times w. If I wanted, I could rewrite that as maybe 2/5 of 1,000 w minus 3w squared.
Wow. Why would you
But
want to do that?
you don't have to. You can distribute the 2/5. Whatever. So that's 5 with 200. 400 w minus 6/5 w squared. You have to do all that distributed. If you wanted to, you could just left it. But I'm not done with the problem. All I've done is written my objective function. My objective function. What are we trying to do with this objective function?
Maximize it.
X, right? So
Optimize.
to do that, I've got to find the critical values, but I also need a domain. So let's pause for just before we get too far ahead of ourselves. I need a domain for this function. So since w is my variable of interest, I have to tell what w value. So w is the element of what interval of numbers. So I'm using w as my independent variable. So what would be the smallest value you could imagine for w being?
1.
0.
0.
In a weird sense, you could have a field that has 0 width, but not exactly. That would make no sense. What we'll do is we'll make an open interval at 0.
Yeah. See, the thing is, it's not a fence, it's a wall. It's a metaphor.
What's the maximum that w could be in some sense? If there was no length to this field, what would be the maximum that w could be?
1,000.
1,000.
1,000.
Or would it be?
1,000 divided by 3, because you got to have 3 w's in there. So, y'all follow how we got that? So we kind of went to the extremes. We went to a 0 width, and I can't really have a 0 length, so I would have to also have a open end on that, which is going to change how I evaluate this problem, which we haven't discussed. We talked that there are open intervals, open circles way up there. How do we actually deal with that? That's what we're going to do right now. So the next step of the process, I guess I need to move overboard, is to find the derivative and find the critical values. Okay, so a prime of w is equal to 400 minus 12/5 of w. So that means it's critical if a prime is equal to 0 or a prime does not exist. That's not going to happen this time. Equal to 0 means that w is going to equal, what is that, 2,000 over 12?
Is that right?
Yes.
Okay.
5 by 4, that's 500 over 3. Okay. I found a critical value, and I have a domain. So what I want to do is test the endpoints and the critical value. But the problem is the endpoints are not included. These endpoints are not included. So I can't just evaluate. I can't do a of 0, so to speak. So what I'm going to do is, since 0 is not in, I can't just plug it in, so I'm going to do a limit. Limit W approaches 0 from the right, since 0 is the left endpoint of my interval, of the function A. Of A. A of W. Which equals the limit. W approaches 0 from the right of 400W minus 400W minus 6/5 W squared, which if W gets close to 0, then this comes out to be a 0. Okay, clear. And similarly, since not always going to be the case, you have open endpoints, but on this one, you have both of them open endpoints. So since 1,000 over 3 is not in the interval, then once again, I can't just plug in. I have to do the limit. I'm not going to 0 now. I'm going to 1,000 over 3 from the left of A of W. Limit W goes to 1,000 over 3 from the left of 400 W minus 6/5 W squared. So what happens when you get 1,000 over 3 for W? This is a continuous function, so I ought to be able to just plug in by my continuous theorem for limits. I'm with a calculator helping out there. 400 times 1,000 over 3 minus 6/5 times 1,000 over 3 squared.
It's a pretty hideous number. Yeah.
Might be 0 again, I guess. Oh. 0? Okay. And then finally, we're going to evaluate at the critical point. So A of 500 over 3 is, so I'm doing my, this was an endpoint. I did another endpoint. Now I'm going to do all of my critical values. That's how you're going to do it every time, except if the endpoint is included in the domain, then if the endpoint is included in the domain, then you can just plug it in. If it's not included in the domain, you have to do a limit. Anyways, what's this number come out to be? If you do A of 500 over 3. Did I get a number yet?
It's all
great. It's like 33,333. 33,333 and a third. Okay. 0.332. That sounds reasonable to me. I don't know. What does that tell me?
If you used a width of 500 for 3,
what length would we use?
33,000.
That was the width. How do I find my length? Right there tells me the length. What's my length? 300? 200. Maximum area 33,333 and a third square. Got it. Make sure, let's double check. Make sure that this number width times that number length calculates that area right there.
Can we zoom in?
Huh?
Can we zoom the camera in on the answer? Yeah.
Oh, sweet.
Right. Did y'all hear my suggestion for a double check on this one?
Yes.
Calculated a width, and then we use that width to calculate a length over here, and then the function gives us the area. So I just wanted to double check that all of my arithmetic and calculator keystrokes have been correct. So if I multiply my width times my length, then I should get my area, and it does come out. It's good. Here's one. We might have time to get one more up. Let's see. Let's make up a problem for us to work on. I'll go back over here. Okay, so suppose we want to minimize cost of forming a soft drink can. Well, let's put cost of materials or forming. I'm not going to minimize the actual forming cost. That involves die stands pressing out chunks of metal and stuff. We won't worry about that. I just want to minimize the materials for the soft drink can. Let's say that what do I want? What information do I need? Okay, so materials for the side and bottom cost $0.1 per square inch. Material for the top cost the top has to be a different kind of structure and thickness to handle having a pop top and all that kind of stuff. Also has to be formed onto it to be sealed. The bottom and the sides all of the same kind of material, just kind of structurally bent into the right position. Okay, so let's see, what else do we might need to know? Let's say that we want, we need this not, but I'm going to say we want
the whole time. Yeah.
the height to always well, twice the radius. And maybe maybe we don't need that, but we also need volume. This might be something I don't need, but I do need the volume. The volume must be, I don't know, what's the volume of a can of soda? I'll make up some number here real quick.
You want a cylinder? Just a straight cylinder. Like no little indentions.
Big, so what is that?
Right.
Let's say volume must be
Hey, Brittany. How long was
3 inches. Again, this, I don't know if this is going to be needed or not. We'll hold on to that one. I think.
What is the volume?
So let's see if we can, how far we can get with this now in the remaining time. So we want to do what? Minimize costs? Is that what it says?
Oh, yeah.
Our objective is to minimize cost.
Joe, could you move the camera to the right a little bit?
Right, just a little bit. There you go.
Better?
Is that better?
That's good, thanks.
Minimize cost. Then we want to some kind of constraint. Any constraint I'm looking at right here is that the volume is equal to 80 cubic inches. Then we need some kind of a domain. I don't know that yet. I gotta write an equation for I can even have a domain. So how do we even begin to attack costs? How do you figure out the cost of the materials that go into this can? It would be helpful if we visualize a can.
I have it in my hand. You know, it looks like a U to me, I'll be honest with you.
What a can looks like?
Eh, I'll take it.
If we break it apart into tops and bottoms and sides, what do you see? Well, you've got a top that's a circle. Got a bottom that's a circle.
Mm. Well, you got a
Where do the
rectangle?
sides come from?
You want a rectangle?
Right? Right, so we got a rectangle here. That's going to be called the side.
Wonderful.
So, starting with that, I ask the question again. How do you determine the cost of the materials to make this can?
Top costs 25 cents, and the sides cost 1 cent.
Yes. So you got to know, it's not that this costs 25 cents. It costs 25 cents per square inch. So what does that mean I need to know?
You need to know your area or something like that.
Yeah, so if I was going to write a cost function over here maybe.
What?
So it looks to me like cost equals 25 cents times the area of the top plus 1 penny times the area of the side plus area of the bottom.
Oh, damn.
So agree that's how I calculate my cost? A big picture way. How we get into the details, the weeds as they call them nowadays. How do I determine the area of the top?
You're gonna use the circle formula.
Okay, so what's that gonna be?
Pi r squared. Got him.
I'm gonna guess that's also how you calculate the area of the bottom. The area of the side. Well, I don't need that.
Squared.
Yeah, area of the side is just going to be length times width. That's right, length times width.
LW. You gotta solve for W here.
And then
Okay, well, let's put L times W over here. See what that does for me. L times W.
Means win.
Now, how many variables do I have in my equation?
3.
Three.
3.
For L and W, but I only need one, so we got to do something about that. So, Oh, the W might be the height of the can.
Dang.
So we could change that to the height of the can. What about the length?
That's the circumference or something like that.
Say again, Rizzo.
Is it circumference?
It's circumference. How do you calculate circumference?
Pi d, right?
Pi times d. Since I'm already using r, then I'll use 2 times pi times r instead of pi times d, but they're equivalent. 2r
That's
makes
really
d.
Wow.
Now how many variables do I have?
2.
2, r and h. I'm still not quite there. But I haven't used a piece of information in case you missed it over at Davidson. I walked back over here to the other board a moment ago, and I erased that thing I circled when I said, I don't know if I need this or not. I decided I don't need it because I've got this. Volume must be 80 cubic inches. How can I use that constraint? This is my constraint. Finishing this into a single variable. Volume equals 80 cubic inches. How do you calculate volume of a soda can?
Pi r squared times height.
Oh my gosh.
Yes. Volume of any kind of what we call a parallel pipe bed, and this is a circular one, is you have the area of the base times the height gives you the volume. Whatever the shape, if you got parallel bases that are the same shape, and sides connected, you take the area of that base, whatever that base shape is, times the height, you get the volume. So volume equals area of the base times the height. Well, this time the area of the base, I don't know who said it. Was it Sammy that said it, or?
Sandy.
I mean, yes. So the area of the base is pi r squared, and then times the height is the volume. Well, since the volume is 80, I was given, then I can figure out what, say, h is in terms of r, or r is in terms of h. I think it'd be easier just to h equals 80 over pi r squared. So now I've got an equation that's down to one variable.
This is
All right, if it were me, I would clean that up before I start trying to do derivatives on it. I also have to think about domain. Cleaning it up, I've got a pi. Let's see, this doesn't have a pi. That cancels the pi, so I can't factor pi out of that. But over here on these r squared terms, I could. Let's see, so I got 0.01 and 0.25, so I got 0.26 times pi times r squared. Plus, and then I've got 280 is 40 R squared cancels with an R, so I get 40 times 0.01 is 0.4 over R. That's not too bad. That cleaned up pretty nice.
Where to get the
So I,
from?
in here, 2 times 80 is not divided, so that's 160. So this is 1.6. And then the R's cancel, leave an R on the bottom. Okay, so that's simplified. I can do derivatives. We have to talk about domain real quick. Don't follow that out. I just combine these two together with that to make this. And then I just simplified all of this together with that, get that. Okay, now domain issue real quick.
Times 2. Yeah.
What's my variable of interest here?
1.01.
Variables in my function. This can be written as cost of a variable. So I need to know radius is an element of what interval of numbers? Radius of my can. Well, the smallest it could be in some theoretical sense is 0, right?
Oh my gosh.
I can really use 0. This time I definitely can't use 0. Why can I definitely not use 0 this time?
Because it makes no
Divide.
sense.
There would be no.
But it makes no sense in the real world, plus I'm dividing by it, so in the theory world, I still can't use it.
Holy crap.
What's the maximum I can use for R?
80 inches.
Remember last time, what did we do? We looked at the minimum of W was 0, and then we looked at length being 0. What did that give me for W? Remember that game?
No.
Same game here. So go back up here. What if the height were somehow shrunk to 0? Height was shrunk to 0. What would that mean about R? Well, or look right here. What would it take if H went to 0 right there? What would it take this R to be to make this turn into a 0? R would have to be infinity, folks. Infinity.
Oh yeah. So we have an infinite radius.
Oh, my interval is from 0 to infinity.
I get
Once
it.
again, you're not going to be able to plug in the endpoints on this one because they're open-ended. And one of them is infinity, so you definitely can't plug it in. So you'll have to do limits. But likely, the critical point will be the local max once you find the critical point right here. I just forgot our timeline. Okay. So for homework, I've posted some problems, several problems, a bunch of problems actually, in 3.4. A bunch of those, try to get them worked out. The hardest part, literally, folks, is like always, is the translation from the English math. Once you translate the English words into a math equation, it's usually not that bad. Like to have an English to Spanish dictionary. If you had a English to math dictionary, wouldn't that be nice? Right. See you all tomorrow.
Did you do it for the limits?
For example, tomorrow we'll pick up. Question.
Number is that 1.6 overall?
I think that's a 1.6 unless I did my arithmetic wrong.
I thought it was.
Let's check it. Let's check it. Let's see. So 2 times 80 is 160. I don't even need a calculator for that. If you multiply it by 0.01, that means you gotta move the decimal points less than 1.6, I think is right. At first, I divided by 2 for some reason, put a 40 there in my mind. That was wrong, it's actually multiplied by.
I will only be there for part of it though, because it's very big initiative. So,
Wait, when are you guys handing out the stress?
it'd be from 11.
I did not go
to
there.
That's really sad. So we'll get done with stress ball.
Wait, well, currently I was at home, and now I don't
I'm
have
done with the stress balls at 12.
I mean, I've got one pencils and stuff, but they're not good pencils and they're not good pencils. And I was having a great day, so I'm just gonna invest in
So,
floor.
in fact, about 170 students at our school that are not counting 100 dropouts, like that still has Samantha Joyner and all of them. So, I decided to overestimate a little just in case, and it got lost, or some were default, or some were just.
The stress balls? Oh, you're bringing them to the county office?
Yeah. So I ended up getting, I had my mom order 200, just so it's 25 extra, right? Just in case some came and they were broken or not.
Man, I look really Filipino.
And then my mom didn't know that I ordered extra, so she ordered extra. She got 25 extra, so I'm stuck with 50 extra balls at home.
Hey, you should give me.
22 people at the county office, and I was like, why would you put them out there? Because Ashley sent them an email saying I was bringing them down. I'm bringing them down.
What were you guys saying about me and
I got confused. I thought you guys said 5.
Yeah, that's all we said.
uh,
And you made it a big deal.
it was funny though.
95 's a
I
little better.
guess, just a
When
little
you were
bit.
laughing about it, so I assumed it was funny.
What's the deal with that?
Or it could just be like Malcolm and me, and we just laugh about literally nothing.
So when you start teaching Taekwondo,
Did Elise drop out?
I don't know.
I don't see her.
Sorry, we actually didn't know how many people would be in here. Really, we can't run a class with less than 10 people. And so this class really